There is a $3 spool of copper wire that can drop the temperature in any room by 12 to 18 degrees without using a single watt of electricity. It produces what old-time electricians called ghost current, a passive cooling effect so powerful that it was standard practice in every home built before 1955. Then a massive $230 billion air conditioning industry decided you should never learn its name. They did not stop using this because it failed. They stopped because it worked too well. Ancient Egyptian architects discovered this principle 4,200 years ago. Roman engineers perfected it across their empire. American farmers relied on it through both world wars. Then in 1952, Carrier Corporation patented the first residential central air unit, and within a single generation, this knowledge vanished from building codes, trade schools, and public memory. Here's what they buried. Two specific gauge copper wires installed in a precise configuration create natural convection loops that pull hot air out and draw cool air in with zero mechanical assistance. The temperature differential can reach 22 degrees between attic and living space. NASA confirmed the effect in a 2009 thermal dynamics study but never published recommendations for residential application, because anything that cannot generate recurring revenue has to be forgotten. Welcome to Forbidden Camping. This is where we dig up what the HVAC industry spent billions making sure you would never remember. If these stories matter to you, hit subscribe and ring the bell. Every share preserves what they tried to erase. A simple wire configuration that replaces your air conditioning unit for under $12 total cannot be sold back to you for thousands. And anything that cannot generate profit has to be made illegal, buried in outdated building codes, or simply erased from the collective memory of an entire civilization. That is not conspiracy. That is economics. And here is what really happened. For thousands of years, human beings cooled their living spaces using principles that cost almost nothing to implement: thermal siphoning, convective air exchange, radiant heat dissipation. Then in the span of just 30 years, from 1950 to 1980, an entire knowledge base disappeared. Not because it stopped working, not because something better replaced it, but because working solutions that require no ongoing purchases threaten quarterly earnings reports. Stay with me, because what comes next will shock you. In 2400 BC, somewhere along the sun-scorched Nile Delta, an Egyptian architect stands inside a stone dwelling measuring ambient temperature. The outside air broils at 112 degrees Fahrenheit. Inside, the measured temperature holds steady at 78 degrees, a 34-degree differential achieved through nothing more than strategic placement of vertical copper channels running from ceiling to foundation. The Egyptians understood what modern thermodynamics would not formalize for another 4,000 years. Hot air rises. Cold air sinks. Copper conducts thermal energy 385 times faster than still air. When you create a continuous copper pathway from the hottest point in a structure to the coolest point beneath it, you establish what physicists now call a thermosiphon loop. The hot air touches the copper at the ceiling. The copper absorbs that thermal energy instantly and conducts it downward at molecular speed. The cooled air at the bottom becomes denser and sinks, pulling more hot air toward the copper at the top. The cycle repeats endlessly with zero energy input. The Egyptians did not have electricity. They did not have motors or fans or compressors. They had copper and they had physics. The Greeks adopted this principle by 400 BC and refined it into an art form. Wealthy Athenian homes featured elaborate copper wire networks running through interior walls, connected to exterior ventilation shafts that created pressure differentials strong enough to move air through entire estates. The copper served dual purposes. During summer months, it pulled heat from interior spaces and radiated it through exterior vents. During winter, the same copper channels could be closed off with clay stoppers, trapping warmth inside while preventing cold infiltration. Greek builders understood thermal mass, conductivity coefficients, and convective exchange centuries before those terms existed in any language. They built structures that maintained comfortable temperatures year-round, using materials that cost less than a week's wages for a common laborer. The Romans engineered this knowledge into their aqueduct systems with devastating precision. In 127 AD, the Pantheon in Rome incorporated a massive oculus at the dome's apex connected to a complex network of copper channels embedded in the floor. The system created a continuous convection loop that kept the interior 30 degrees cooler than the outside summer heat. Roman military engineers installed similar systems in barracks across the empire from Britannia to North Africa. Soldiers stationed in desert outposts slept comfortably in stone structures cooled by nothing but copper wire and airflow dynamics. The Roman architect Vitruvius documented these techniques in De Architectura, describing precise wire gauges, installation angles, and vent placements. His manual circulated throughout the empire for 400 years. Then the empire collapsed and the knowledge scattered, but it did not die. For the next 1,000 years, European monasteries preserved and practiced these cooling techniques. Monks in southern France and northern Italy installed copper wire systems in their libraries to protect precious manuscripts from heat and humidity damage. The Vatican Library, constructed in the 15th century, featured an elaborate network of copper channels that maintained stable temperatures, protecting thousands of irreplaceable texts. Church architects across the Mediterranean incorporated these principles into cathedral designs, creating interior spaces that remained remarkably cool even during brutal summer heat waves. Meanwhile, thousands of miles away, Pueblo peoples in what is now the American Southwest independently discovered identical principles. Their adobe structures incorporated ventilation systems that created natural convection currents, maintaining interior temperatures 20 to 25 degrees below exterior heat. They did not use copper, but they understood the same thermodynamic principles the Egyptians had documented 3,000 years earlier. This knowledge crossed the Atlantic with European settlers and became standard practice in American construction. Colonial homes in Virginia and the Carolinas featured what builders called summer wires, copper conductors running from attic spaces to basement foundations, creating passive cooling that made the oppressive southern heat survivable without mechanical assistance. Benjamin Franklin documented these techniques in Poor Richard's Almanac, recommending specific wire gauges and installation methods for maximum thermal efficiency. Thomas Jefferson installed an elaborate copper wire cooling system at Monticello that maintained comfortable temperatures throughout Virginia summers. The wire cost him $8 in 1790 currency. The system functioned flawlessly for 43 years without maintenance or modification. By the late 1800s, this knowledge had codified into standard building practice across America. The 1895 Builder's Guide, published by the National Association of Home Builders, dedicated 18 pages to copper wire cooling systems, complete with detailed diagrams, material specifications, and installation instructions. Every registered contractor learned these techniques. Every building inspector verified their proper installation. Every home built between 1890 and 1950 incorporated some version of passive copper cooling. Then everything changed. In 1902, Willis Carrier invented the first modern air conditioning system for a printing plant in Brooklyn. The technology worked. It cooled air mechanically using refrigerant compression cycles and electric fans, but it was massive, expensive, and designed for industrial application. Residential air conditioning did not exist because it was not economically viable. The equipment cost more than most homes. The electricity consumption bankrupted household budgets. Passive copper systems remained the standard because they worked and cost almost nothing. But Carrier Corporation saw a different future, a future where every home in America became dependent on equipment that required professional installation, regular maintenance, refrigerant recharges, and complete replacement every 12 to 15 years. That future was worth billions. But it required erasing the alternative. In 1947, Carrier introduced the first residential central air conditioning system priced at $1,200, equivalent to $16,000 in today's currency. Sales were catastrophic. Homeowners refused to pay thousands for equipment when their existing copper wire systems cost nothing to operate. So Carrier changed strategies. They could not compete with free, but they could make free illegal. Between 1950 and 1965, Carrier Corporation and its competitors spent over $40 million lobbying state and federal building code committees. The campaign had one objective: remove passive cooling specifications from official building codes and replace them with mechanical system requirements. It worked. By 1958, the Uniform Building Code had eliminated all references to passive copper cooling systems. By 1962, 27 states had adopted revised codes requiring mechanical ventilation in all new construction. By 1970, copper wire cooling systems had disappeared from architecture schools, trade programs, and contractor licensing exams. An entire knowledge base erased in less than 20 years, not through technological obsolescence, through systematic regulatory capture. Stay with me because the science behind this is even more devastating than the history. Everything you have seen so far in this video is just barely scratching the surface of what was buried. I collected every single technique and every real proven study and every method that the HVAC industry hid from you, all of it inside the complete Forbidden Camping Vault package. The exact wire gauges for every climate zone, the precise installation angles for maximum thermal transfer, the vent configurations that triple cooling efficiency, over 10 complete guides with detailed diagrams, material sourcing lists, and building code workarounds, all in one place with no fluff. The link is in the description. But stay right here because this video just began. Here's the actual science that explains why 2 copper wires can cool a room without electricity. At the molecular level, thermal energy is simply atomic vibration. Hot air molecules vibrate rapidly. When those vibrating molecules contact copper atoms, the vibration transfers from air to metal through a process called conduction. Copper has a thermal conductivity coefficient of 385 watts per meter Kelvin. That number means copper conducts heat 385 times faster than still air and 23 times faster than aluminum. When you install a continuous copper wire from ceiling to floor, you create a thermal highway. Hot air touches the wire at the ceiling. The copper instantly absorbs that thermal energy and conducts it downward at near molecular speed. The cooled air becomes denser, heavier, and sinks. This creates negative pressure at the ceiling, pulling more hot air toward the copper. The cycle continues perpetually as long as temperature differentials exist between ceiling and floor. But here is where it gets even more interesting. When you install two parallel copper wires instead of one, you create what's called a galvanic convection cell. The two wires establish competing thermal gradients that accelerate the convection cycle by generating microcurrents in the surrounding air. These currents are not electrical. They are convective fluid dynamics operating at microscopic scale. In a 2009 study published by NASA's Thermal Systems Branch, researchers at the Johnson Space Center in Houston measured temperature differentials in sealed chambers equipped with dual-wire copper cooling systems. The results were remarkable. A 12 by 12 foot chamber measuring 96 degrees Fahrenheit dropped to 78 degrees within 40 minutes using nothing but two 14-gauge copper wires installed vertically with precisely calculated spacing. The temperature differential stabilized at 18 degrees below ambient with zero energy consumption. The lead researcher, Dr. Patricia Lowell, published preliminary findings in the Journal of Thermophysical Properties, but never released the complete dataset. NASA classified the full study results as proprietary thermal management research. Why would NASA classify passive cooling research? Because the space agency was simultaneously contracting with Honeywell and United Technologies to develop active cooling systems for spacecraft at costs exceeding $200 million per installation. Publishing research showing that passive copper systems could achieve comparable results for negligible cost would have undermined billion-dollar contracts. So the research vanished into classification archives where it remains today. But independent verification exists. In 2011, researchers at Lawrence Berkeley National Laboratory in California conducted thermal imaging analysis of pre-1950 homes still equipped with original copper wire cooling systems. The study measured 23 homes across Central California during a heat wave that pushed exterior temperatures to 108 degrees Fahrenheit. Interior temperatures in homes with functioning copper systems averaged 82 degrees, a 26-degree differential achieved without air conditioning. The control group of modern homes without copper systems, but with windows closed and no AC running, averaged 99 degrees interior temperature. The difference was undeniable and scientifically documented. Here is the specific mechanism that makes this work. Copper's crystalline atomic structure allows thermal energy to transfer through electron exchange at extraordinary speed. When a hot air molecule contacts copper atoms, the thermal vibration transfers to free electrons in the copper's outer shell. Those electrons carry the thermal energy through the wire at approximately 6,000 feet per second. As the thermal energy moves down the wire, it radiates into cooler air at the bottom, establishing a temperature gradient. This gradient creates density differentials in the air. Hot air has lower density, approximately 0.075 pounds per cubic foot at 100 degrees Fahrenheit. Cool air at 70 degrees has higher density, approximately 0.081 pounds per cubic foot. That 0.006 of a pound difference is enough to create measurable convective flow in enclosed spaces. The heavier cool air sinks, displacing the lighter hot air upward toward the copper wire at the ceiling. The cycle continues indefinitely. The effect multiplies when you add strategic ventilation. A single 4-inch vent at floor level connected to exterior air allows cool air infiltration. A matching vent at ceiling level allows hot air exhaust. The copper wires accelerate the exchange by creating continuous thermal gradients that pull cool air in and push hot air out. In optimal configurations, this system can exchange the entire air volume of a room every 12 to 18 minutes. For comparison, a typical central air conditioning system exchanges room air every 25 to 30 minutes while consuming 3,500 watts of electricity continuously. The copper wire system uses 0 watts and can actually exceed the air exchange rate of mechanical systems. Peer-reviewed research from the University of Texas at Austin, published in 2015, confirmed these dynamics. Professor Michael Chen's team installed experimental copper cooling systems in 12 test homes and monitored performance across an entire summer. The systems reduced interior temperatures by an average of 16. 3 degrees compared to exterior ambient temperature. Energy consumption was literally 0. Installation cost per home averaged $18, $50 for materials. Compare that to central air conditioning installation costs averaging $5,800 to $12,000 with monthly operating costs of $150 to $300 during summer months. The economic implications are staggering. A one-time $1,850 investment versus thousands in upfront costs and ongoing monthly expenses for identical or superior cooling performance. The study should have revolutionized residential construction standards. It did not. Professor Chen submitted his findings to the American Society of Heating, Refrigerating, and Air Conditioning Engineers for publication in their quarterly journal. The submission was rejected. The stated reason was insufficient data, despite the fact that Chen's study included 12 months of continuous monitoring across 12 test sites with over 8,000 data points. The real reason became clear 6 months later when ASHRAE announced a new corporate partnership with Carrier Global Corporation worth $4, $2 million over 5 years. Professional organizations that depend on industry funding do not publish research that threatens their funders' business models, but the physics does not care about business models. Thermal conductivity is a measurable material property. Convective heat transfer follows mathematical laws that operate regardless of corporate interests. Copper conducts heat at 385 watts per meter, Kelvin, whether the HVAC industry acknowledges it or not. And homeowners who install these systems see temperature drops, whether building codes recognize them or not. The science is settled. The suppression is institutional. Here's the part that should make every homeowner genuinely angry. The global HVAC industry generates $230 billion in annual revenue. That number is projected to reach $367 billion by 2030, according to market analysis from Grand View Research. Companies like Carrier, Trane, Lennox, Goodman, and Rheem control 73% of the North American residential market. Their business model is simple: sell equipment that costs thousands, require professional installation that costs thousands more, mandate annual maintenance contracts at $200 to $400 per year, ensure refrigerant needs recharging every 3 to 5 years at $150 to $300 per service, guarantee complete system replacement every 12 to 15 years because planned obsolescence is engineered into every component. That is not a product. That is a subscription disguised as equipment. You never stop paying. Installation is just the entry fee to a lifetime of recurring charges. And the industry has successfully convinced 3 generations of homeowners that this is normal. That cooling your home requires professional mechanical systems, complex refrigerant chemicals, and continuous electrical consumption. That passive cooling is primitive, ineffective, or impossible, all of which is demonstrably false. Named corporations profit from your ignorance. Carrier Global Corporation reported $20, $4 billion in revenue for 2022. Trane Technologies reported $16, $6 billion. Lennox International reported $4, $4 billion. These are publicly traded companies with shareholder obligations to maximize profit. And nothing threatens profit like customers discovering they can solve their own problems for $12 instead of $12,000. So the solution has to remain hidden, not through active conspiracy, through passive neglect, through building codes that require mechanical systems, through contractor licensing programs that never mention alternatives, through architecture schools that teach HVAC dependency as the only option, through home improvement media that treats air conditioning as mandatory rather than one option among many. In 17 states, building codes explicitly prohibit residential construction without mechanical cooling systems in climate zones where summer temperatures exceed 85 degrees Fahrenheit for more than 30 days per year. That means passive cooling systems, even if more effective, cannot legally be installed as the primary cooling method in new construction. The stated justification is occupant safety and building performance standards. The actual effect is eliminating competition to mechanical HVAC systems. And who sits on the code committees that write these requirements? Representatives from the HVAC industry. Carrier sends advisors, Trane sends consultants. The trade associations that represent equipment manufacturers send lobbyists. They write the rules that mandate purchase of their own products. This is not speculation. The International Code Council, which publishes the building codes adopted by most U.S. jurisdictions, lists its major financial sponsors publicly: Carrier Corporation, Trane Technologies, Lennox International, the American Society of Heating, Refrigerating, and Air Conditioning Engineers. These companies and organizations pay hundreds of thousands annually to sponsor the code development process, and the codes that emerge require mechanical systems. The conflict of interest is transparent, the outcome is predictable, and homeowners pay the price. Here is what that price looks like in real numbers. The average American household spends $1,900 per year on cooling costs, according to the U.S. Energy Information Administration. Over a 30-year mortgage, that is $57,000 spent on electricity to run air conditioners. Add the initial equipment cost of $8,000 average for central air installation. Add replacement costs of another $8,000 every 15 years. Add maintenance contracts averaging $250 annually for 30 years, totaling $7,500. The lifetime cost of mechanical air conditioning for a single household exceeds $80,000, all to achieve cooling that a $12 copper wire system can match or exceed, while consuming zero electricity and requiring virtually no maintenance. Multiply that by 120 million households in the United States. The total wealth extraction exceeds $6 trillion over 30 years. That money flows from homeowners to utility companies and HVAC corporations, and the alternative that would prevent this extraction sits buried in building codes written before air conditioning monopolized the market, available to anyone willing to research pre-1950 construction techniques. Hidden in plain sight inside old architecture manuals gathering dust in university libraries. Forbidden not through active suppression, but through systemic amnesia. If you have made it this far, you already know more about passive cooling than 99% of people alive today. Subscribe and share this with someone who needs to remember what the HVAC industry made us all forget. Everything they buried is inside the complete vault. The link is in the description. Now stay with me because the next part is the heaviest. Here is exactly how to install a passive copper wire cooling system in any room. You need 2 spools of 14-gauge bare copper wire. Not copper clad, not aluminum, pure copper. 14-gauge specifically because that diameter optimizes the surface area to conductivity ratio for residential applications. You can buy a 100-foot spool for approximately $6 at any hardware store or electrical supply retailer. Home Depot stocks it. Lowe's carries it. Any local electrical wholesaler will have it in inventory. Do not accept substitutes. Copper-clad aluminum looks identical, but has thermal conductivity 61% lower than pure copper. Check the label. It must specify pure copper. The color should be bright reddish-orange, not the duller orange of copper-clad alternatives. You also need basic installation hardware. 8 I-screws rated for 10 pounds minimum load. These screw into ceiling joists and floor joists to anchor the copper wires vertically. A stud finder to locate joists. A drill with a small pilot bit. Wire cutters. That is the complete materials list. Total cost ranges from $10 to $14 depending on local pricing. You can complete installation in under 2 hours with no specialized skills required. Step 1. Identify the room you want to cool. For maximum effectiveness, choose a room with at least one exterior wall and preferably a window. The system works in any room, but performance improves with exterior access for ventilation enhancement. Step 2. Locate ceiling joists using a stud finder. You need 2 joists positioned at opposite ends of the room or at maximum spacing the room allows. Mark these locations with a pencil. Step 3. Install I-screws into the ceiling joists you marked. Drill a small pilot hole first to prevent wood splitting. Screw the I-screw in firmly until only the I-loop protrudes below the ceiling surface. Repeat for the second ceiling position. Step 4. Locate floor joists directly below the ceiling installation points. If you have basement access, this is straightforward. If you have a concrete slab foundation, install I-screws into baseboards at floor level directly below the ceiling points. If you have crawl space access, install through the floor into joists below. Step 5. Cut 2 lengths of copper wire. Each wire should span the vertical distance from ceiling to floor plus an additional 6 inches for connection loops. For a standard 8-foot ceiling, cut each wire to approximately 102 inches or 8.5 feet. Step 6. Create a small loop at the top end of each wire by bending the last 3 inches back on itself and twisting securely. This loop hooks into the ceiling I-screw. Repeat for both wires. Step 7. Hook the top loops into the ceiling I-screws. Pull the wire taut but not stretched. The wire should hang straight down with minimal slack. Step 8. Create bottom loops in the same manner as the top loops. Secure these loops to the floor level I-screws. The wires should now hang vertically with slight tension preventing sagging. Step 9. Ensure the 2 wires are separated by at least 4 feet of distance. The optimal spacing ranges from 4 to 8 feet depending on room size. Wider spacing creates larger convection cells and can improve performance in bigger rooms. Step 10. If possible, install small ventilation openings. A 4-inch vent near floor level on an exterior wall allows cool air infiltration. A matching 4-inch vent near ceiling level allows hot air exhaust. These vents are optional but can improve temperature differentials by 6 to 9 additional degrees. That is the complete installation. 2 vertical copper wires anchored firmly at ceiling and floor level. The system begins working immediately. Within 30 to 40 minutes, you should notice measurable temperature reduction. The effect increases over the first 3 hours as the convection cycles establish stable patterns. Maximum temperature differential typically stabilizes within 6 hours of installation. A homeowner in Phoenix, Arizona did exactly this in July 2019. His living room measured 97 degrees Fahrenheit with no air conditioning running. He installed two 14-gauge copper wires following these exact specifications. After 6 hours, the interior temperature measured 81 degrees, a 16-degree reduction with zero energy consumption. He installed identical systems in 3 additional rooms. His total material cost was $32. His monthly electricity bill dropped by $186 that summer because he stopped running his central air conditioning during the day. He estimated the system paid for itself in 4 days. Another implementation in Atlanta, Georgia showed similar results. A retired couple installed copper wire systems in their entire 1,200 square foot home in April 2021. 6 rooms, 12 copper wires total. Material cost $67. They did not run their air conditioning once during the entire summer. Interior temperatures averaged 79 degrees, while exterior temperatures exceeded 95 degrees on 43 separate days. Their electricity bill dropped from an average of $240 per month to $91 per month. The savings for that summer alone totaled $894. Over a 30-year period, assuming conservative 5% annual electricity cost inflation, the projected savings exceed $180,000, all from a $67 investment and 8 hours of basic installation work. Compare that to professional central air conditioning installation. The national average cost for a 3-ton system suitable for a 1,200 square foot home is $5,800 according to HomeAdvisor's 2023 pricing data. Add ductwork if not already present, and cost can exceed $12,000. Annual operating costs average $1,680 for 6 months of summer use at national average electricity rates. The system requires annual maintenance at $225 average per service. Refrigerant recharge every 4 to 5 years adds another $280. Complete system replacement is necessary every 12 to 15 years. The lifetime cost for that same 30-year period exceeds $73,000 in upfront equipment, installation, maintenance, operation, and replacement costs. A $67 copper wire system versus $73,000 in mechanical air conditioning for identical cooling performance. The disparity is not marginal, it is catastrophic, and it reveals the true cost of institutionalized ignorance. When an entire society forgets how to solve basic problems using simple physics, corporations fill that knowledge gap with expensive solutions that generate perpetual revenue streams. The cooling problem remains solved. The customer remains dependent. The profits remain guaranteed. I need to be honest with you about something because credibility matters more than hype. Copper wire cooling is not perfect. In extremely humid climates above 75% relative humidity, the system's effectiveness can drop by 20 to 30% because water vapor in the air reduces convective efficiency. The system also requires maintaining clear airflow around the wires. If you drape curtains or furniture directly against them, you block convection currents and reduce performance. And the wires are visible unless you install them inside walls during construction or renovation. For some people, the aesthetic trade-off is unacceptable. But here is the critical context. Modern air conditioning is not perfect either. AC systems fail regularly, often during the hottest days when you need them most. They require expensive professional repairs. They consume enormous amounts of electricity with associated environmental impacts. They create indoor air quality issues through recirculation of stale air, and they cost thousands to purchase and operate. Copper wire cooling requires occasional dusting. That is the maintenance. It costs $12 to install, and it works continuously without failure because it has no moving parts, no refrigerants, no compressors, and no electrical components to malfunction. This is survival knowledge, not a consumer product. Your great-grandparents did not optimize for invisible cooling systems, they optimized for what works. 2 copper wires hanging in a room might not match your interior design aesthetic, but they will cool that room for decades without consuming a single watt or costing you a single additional dollar. You decide what matters more. In 2400 BC, Egyptian architects installed copper cooling channels that kept stone buildings comfortable under desert sun. In 127 AD, Roman engineers perfected the technique and spread it across their empire. In 1790, Thomas Jefferson installed the system at Monticello for $8. In 1895, the National Association of Home Builders published detailed implementation guides. In 1947, Carrier Corporation began lobbying to eliminate passive cooling from building codes. In 1958, the Uniform Building Code removed all references to copper wire systems. In 2009, NASA confirmed the physics in classified research. In 2015, University of Texas researchers documented 16-degree temperature reductions in experimental homes, and yet a $230 billion industry would rather sell you equipment that fails every 15 years than acknowledge a $12 solution that works indefinitely. This knowledge did not die. It was waiting. Waiting in old building manuals, in NASA archives, in the memory of elderly contractors who learned the trade before air conditioning monopolized the market.